Hello everyone, my name is Hitesh Kapoor. I am a software engineer at DataTorrent, and I will be today giving a small talk on end-to-end exactly once in Apache Apex, how do we achieve it. And this presentation has been co-prepared by Priyanka. She is also a software engineer at DataTorrent. So I will start. So in today's talk, in this talks, we will actually discuss like what is end-to-end exactly once, and the importance of end-to-end exactly once, like how does it becomes important, what are the challenges in getting end-to-end exactly once, and finally I will give an example of how to achieve the final results in Apache Apex, and then I'll conclude by giving some key takeaways, and we can have the questions at the end, or we can have some logical breaks as required. So fault tolerance. I am starting with some basic concepts. I know you all are aware of it, but this concept will just help to ease into this topic. So fault tolerance is nothing but the ability of the system to recover from failures. And in Apache Apex, this feature has been given the prime importance. And it helps us to achieve a stateful recovery of our system. So in this talk, we will basically be discussing about how we recover from an operator or a container failure. So whenever a container fails or an operator fails, we need to recover those. So the recovery mechanisms are nothing but the algorithms that are used to recover from a failure. And even in conventional systems, whenever there is a failure, what do? We will recompute the results. We will start to recomputing the results. In streaming platform engine, to recompute the results, we'll have to replay the data, right? So same as this mechanism over here, we will replay the data. So how we replay the data is of importance over here. So there are three mechanisms to do that. They are known as at most once, at least once, and exactly once. We'll deep down into them in the upcoming slides. So replay the data. So seriously, we are talking from the morning like volume of data. We are 5 GB, 50 GB. Some are talking about terabytes. The previous talk was like sir was saying that he uses 1 million images to do that. So if there is a failure, we cannot actually afford to replay all the data. So we need to have some mechanism to have a stateful recovery of the data. We need to process or restart the process from some logical point. So this is where the role of platform comes into picture. So for providing this in Apache Apex, we have a concept of checkpointing and buffer servers. So what checkpointing does, it will just store the state of the operator, which was last while working in a durable storage. So whenever the recovery will take place, we will get the state of the operator directly from our durable storage. For example, HDFS, that this is a pluggable mechanism. If you hate HDFS, you can write your own pluggable checkpointing mechanism and plug it. And okay, now I have saved the state of the operator. But what about the data? Right? To have a complete recovery, it is not enough to bring back my operator. I need to feed it with the data as well, which was lost. So that data is stored in a place where we term it as buffer server. And buffer server may sound slightly complicated, but it is nothing but a messaging queue between two operators. Okay. So now I will start with which mechanism will affect in which way, like in case of operator failure, in all the three mechanisms, it will subscribe to the upstream buffer server to fetch the data. But from which point it will subscribe will differ in case of the recovery mechanisms. So when I say at most once, the name itself suggests its meaning. At most once will actually be useful when we don't care about lost data. So it will subscribe from the upstream buffer server from the next begin window. Now I know windows are, I'll just give a small pointer. What are windows? They are nothing but temporal boundaries in a streaming data. Okay, we'll not go deep into that, but just for the understanding, that's it. So in at most one, we will subscribe to the upstream buffer server, and all the streams, all the windows will be replayed from the next begin window from there. So where this could be useful. So in our previous talk, as Abhijat was saying that in a match, there were Coca-Cola was like tracking from which part of the stadium is most of the people are drinking Coke and what are the reviews. So in this scenario, if there is a failure in between, and if the operator recovers after some time, it won't actually care about that. It can neglect those thoughts. It can neglect those images because it needs all the fresh data. For that data is probably stale now. So in these scenarios, we can use at most once. So at least once. Now moving on to at least once. This is by far the most used recovery mechanism. What happens in at least once is, again, the operator or the container which has gone down will subscribe to the upstream buffer server, but this time it will not start directly from the begin window. It will go back to the last checkpointed state, right? And from there it will start to fetch the data. Okay, so there may be a scenario like let's say the checkpoint had happened at 50 and the operator had failed at 53 and now the time is 55. So it will start again from 50. So there will be replay of data from 50 to 53. So in at least one scenario, there is replaying of data, so there might be duplicates, and there is a possible recomputation of data as well. Okay, and these are at least once is primarily used in most of the cases where you are data intolerant, like where you cannot afford to lose data.
So the applications have to be worried about deduplication?
No, it depends. Like if your application wants that your data should not be recomputed again, then you have to do something. We will go on to that. That is what is exactly once. So in exactly once again, if there is a failure, the container or the operator which has failed will subscribe to the upstream buffer server, not from the begin window, but again from the checkpointed state, like at least once. But over here, slight care has to be taken. When the data is getting replayed, the recomputations should be such that the end result of those recomputations should be like the computations has been done only once. I know this is slightly confusing. We'll just go to the next slide for this. So when I say recomputation of the data exactly once, so this is an accepted fact that in distributed systems there is no such thing as strictly exactly once. When we in Apex terms say exactly once, what we mean is that we can provide you exactly once in an end-to-end basis in your complete application. Application is nothing but pieces of operators with the streams, DAGs. So on an end-to-end basis, we can provide you exactly once. So the recomputations will be done, but we have to ingest some intelligence into it, so that the effect of those recomputation is such that the operation has happened only once. That the output of the entire DAG or the output of the entire application has been done only once. We will look how do we, yeah please.
So you just said that we will have to take that the computation looks only once. Even if it is recomputing it, it looks like it is once.
Right.
So is it the developer is going to take care, or there is an inbuilt logic?
No, the platform will provide you support to achieve that. But the developer of the operator, developer in Apex is nothing but who develops the business logic, and business logic goes in the operator. So how the business logic and the operator needs to take care of that. So there are mechanisms to do that. We will how Apex facilitates that. Okay. So end-to-end exactly once, like I was telling now, when will it become important is when we are writing to some external systems like databases. We cannot afford to write duplicate records or something like that. Or more so in credit card swipes, right? We cannot afford to deduct money twice. So in those applications, end-to-end exactly once will matter. And what is actually end-to-end exactly once is, if you think over it, it is nothing but a combination of at least once, idempotency, and some logic on the operator side, as I said. It is a combination of all these three terms. we have already looked at what is at least once. Now we will go ahead and see what is idempotency. So I'm very sure you have heard of this term sometime in your life. In mathematics, we had a formula for idempotency. Similar in Apache Apex, idempotency is on the similar lines, that in case of failure, there will be replay of windows. So the windows before the failure, the data that they were containing before the failure should contain the same data after the failure.
Sure.
Right? This is idempotency in Apex terms.
So this is provided by Apex platform?
We provide support to, we provide you mechanisms to achieve idempotency. Right? So the support which I am talking about, we have a utility named as Window Data Manager, which allows us to handle this state, handle this scenario, and to maintain idempotency, the operator will actually need to remember something, like from where it left off, what was it in the last window. So this information we term it as idempotent state. Right? So this is a small joke, analogy with a small joke. I will just take a moment, have some water.
You mentioned about Windows Data Manager.
Right. Right.
That's a GUI or?
No, that's not a GUI. Currently, that's not a GUI. We may have some mechanism in future, but currently it's like an class. It has some properties which you need to tune. Okay. So it helps in basically maintaining the offsets or some information or some which is required to replay of data to maintain idempotency like stuff. Okay. So this is the example which we will take today to understand which part is being, the role of each part in giving us end-to-end exactly once results. So this is a very new example, word count example. So we are just expanding the basic word count example. Over here, the words will be generated from a Kafka stream. There will be a Kafka stream which will have the words. The input from here, the Apex DAG starts. The input is nothing but a Apache Kafka input operator, which will fetch the words from Kafka, and it will give the words to the counter. Counter is nothing but, as I was speaking about Windows. So Apex give you some mechanisms to do at some temporal boundaries. So counter will do nothing, but will just take the words, aggregate the words in a count, and give the count to the store. And store is nothing but it will give the results to a database, and it will store it in the database. So over here, we will see how we will achieve end-to-end exactly once, right from the start. How will we go? So when we have connectors or operators that deal with the external world, these are the most important elements which need to take care of idempotency and exactly one strategy. I am not saying that idempotency should not be taken care by the operators which come in the middle or in the downstream, but the major responsibility for idempotency goes to the input operators. Because when we need to replay the data, input operators are the one who are going to start the stream again. So in Kafka, in our example, so this mechanism can't be tuned for every operator, like every input source in a similar way. Like Kafka will have some different mechanism to store the data, files have some different mechanism, databases have some different mechanism. So in our example Kafka processes the data on itself. We don't need to handle any of it. And we will, as an consumer or an operator, we'll just need to remember the offset for each window, right? First minute. So as I said, for having idempotency over here, the Apache Kafka operator will need to remember the events that were received and which were transmitted until those are committed, until we no longer require them, right? So in our operator, next one. So in our operator, we use a simple consumer. It is one of the consumers of Kafka, and it helps us to track the offsets quite easily. So once we track the offsets, we will just store that offsets in a durable storage as, yeah. So these offsets and windows will be stored together as pairs. Like for each window, what was the offset? And when we will recover, we will make sure that the same data is being going in the same sequence.
This is a Kafka offset or?
Yes, but we need to store that.
Right, but if the source is, let's say, database, OLTP application,
Then we will have to have some different mechanism. For database, we are using the last emitted row, and using that window data manager, we are checkpointing it. This offset mechanism is similar to what we will do while reading from a file. Right? For database, we have some. So again, the complexity or the mechanism will be different for different input sources. Yes. Right. So similar to what we are doing in the input, there has to be some intelligence which we need to put in the output as well. So in our example, when the database or the store operator will get the data, it needs to make sure if there was a failure that it shouldn't rewrite the data again. It needs to ignore that data somehow, right? So in our example, our operator makes use of transactions to handle this. So how it does it? It will store the data in a separate table. Not data, sorry. It will store the window ID in a separate table. And when we will be recovering it, if there is a recovery, we'll first match the incoming window ID with the stored window ID. And if the window ID is less than the incoming window ID is less than the stored window ID, then it is safe to say that we have already stored this data over here. To add on to this, the data and the window ID are written in a single transaction itself, are committed in the same transaction.
Who is generating this window ID?
This is generated in the stream, like right from the input, there is a stream of data going in. So these windows are nothing but control tuples which are emitted as a part of stream.
Right, but when you replay that stream,
Right.
How do you make sure the same window ID is there?
Right. So as I told you, we store the data in a place named as buffer server. So buffer server will be responsible for that. We'll not be going in depth of how it does it, but just to give an idea, buffer server will be responsible for this.
Just to understand in layman terms, this buffer server you're talking about, so this is the point wherein the data is still being held till the checkpointing has been completed or
Yes. Right. It's a PubSub mechanism. So basically it stores in memory, but if required, it will spill over to disk.
is it partition or buffer server?
If your operators are partitioned, I'm actually not sure about that.
So just it is per operator, per container rather. So if you have 3 containers in HANA, it will be 3.
Yeah. So if the operators are in different containers for those,
And you can control for how long duration you want to keep those buffers. Like
the
of
control,
offset.
yeah. So actually, that is a complete different mechanism of buffer server. How do we do that? Is after every operator has reached a particular checkpoint, then all the data before that checkpointing is
Discarded.
flushed. Yeah.
is it that checkpoint the same number that was there in the previous slides, 30 seconds by default?
Yes.
That's the
Yes,
same.
yeah.
So that's configurable.
Yes. Totally configured. Right. Yeah. So just one slide. Yeah. So this operator, which is already we have built it in abstract JDBC transactional output operator, and we have multiple flavors of this. Like the base implementation is multiple flavors of this. We will discuss one of the flavors which we are using in our example. So just to give you a fair idea of this database, I have just noted all the points which I had said. Data is in a window is written out in a single transaction. Window ID is also written to a meta table as a part of the same transaction. So operator will read the window ID from the meta table on recovery, and it will ignore all the data for windows less than the window ID. Okay, so if there was a partial computation of data in a window, it will not be redone because it is never committed, so it will roll back. Okay.
So this logic that you just mentioned holds true even for operators, or does it hold true only for the output operator? So the computational operators like filtering and counting and things like that.
Right.
So do we actually recompute in the intermediate stages?
Right. So wherever there is a failure, all the downstream operators will be, actually we will have to redeploy them again. We do redeploy them again, and this logic is done on every intermediate one.
So the
But-
recomputation is avoided even in the intermediate stages if the window ID.
No. This I'm only talking about the on the output side. For our example,
Yes.
we need to embed this logic only on the output side.
So you're saying that the recomputation will be done on the intermediate stages if the checkpoint, if the state at which the failure happened
Right.
and the last checkpoint point
Right.
has say 4 windows that were persisted in the buffer manager,
Mhm.
but they have not yet been checkpointed, and
Right.
the failure happened after the 4th window.
Right.
So the recomputation will happen for those 4 windows again in the
In the
intermediate.
intermediate, yes. If you don't want it, then you will have to apply some intelligence to it.
In our operator implementation.
Right.
Okay,
The same intelligence which we have applied to our on the JDBC side.
I see. Okay.
So
But-
does the same mechanism work for stateful operators versus stateless operators?
No. Stateless operators will actually, when we say a stateless
It
operator,
is idempotent by default,
Idempotent
right?
yeah. So, but it will not require to do that.
No.
When we say end exactly once, we will talk about end to end exactly once. So whatever is happening, recomputations in between.
No, I was
Ideally-
more talking of optimization from optimization perspective. That's
So,
fine.
yeah. So for that, I can just say that all the data is never replayed. Only the data from the
Which
last
is
checkpointed
checkpoint only
state
is replayed.
will be replayed.
Yes, sure.
So and this is the example which we had took. So we use our operator, and the basically we will just provide it an update query to get it done. So it's very straightforward how we do it. We will use a merge query to do it, and we will just insert the results only when they are not present in the output table, or we will just increment the count. It's very straightforward. Yeah, so how everything is getting tailored together, we'll see over here. How idempotency, how at least once, and how the operator logic comes together and gives us end-to-end results. So in our example, let us say we are checkpointing after every 2 windows. Okay, just forget, like, we will not go in the concepts how we checkpoint after every 2 windows, and I said it is configurable in seconds or so. There is some mechanism to achieve that. So let us say we are checkpointing after every 2 windows. Okay, and let us say this was the scenario before the failure. Window 1 had incoming 1 count is added from the counter operator 2 and is stored in the database as 2. Now this will be committed over here. The output, as I explained, after this store will have 2. Now when window 2 comes, right? Now there is 1, window 2 hasn't finished, and there is a failure, right? So now the store will store 2 over there. Now when the recovery will come into picture. Now let us say the operator is not idempotent. And when I say it is not idempotent, same windows before the failure may have different data. So now let us assume 1 which was appearing in window 1 now goes to window 2. But the store has already committed 2 over there. So it will ignore all the data that was coming before that window ID. So it will ignore this, and it will just add 1 plus 1 plus 1, 3, and store it in the database as 5. Right? So this is an incorrect result. So we need idempotency over here. Of course, we need at least once. If on recovery window 2 is lost, then we can never get the complete result. Right? So when we recover, if we maintain the idempotency, we will get the desired results or the correct results. So I'll just conclude by saying that Apache Apex is the foundation of fault-tolerant systems. It has major emphasis on fault tolerance because how you recover, the efforts it takes to recover also affects your operability. So automatic recovery, statefulness recovery, it has a good focus on those points. And we have a library of connectors that cover many of the integration scenarios like files, HDFS, then Hive. Most of them we have Avro, databases. End-to-end exactly once is nothing but a combination of at least one semantics, idempotency, and some consistent behavior across the operators. And this was the example which we took. We took Kafka to JDBC example. We used an external meta table to store the Windows IDs to assure exactly one strategy for the output table. And these are the resources which most of us have used. So, thank you.